Alright guys, so today we are here with another topic of partial derivatives, and this topic is tangent planes and differentials. Alright, so first of all we would see that what's tangent plane, right? What is the idea of tangent plane? Because in calculus 1 we talked about a tangent line, right? Remember? So in calculus 1 we developed idea of finding tangent line on a particular curve, but here we have some other goal. Our goal is totally different, that we have to find a tangent plane of a given surface. I can say take a surface and find a tangent plane, right? Okay, so let's see how do we find that. All right, so tangent plane touches the surface at exactly one point within our neighborhood, right? So this is the general idea. We have to just know that. How do we play with the tangent planes? All right, so it says that suppose a surface S has equation z is equal to f of x y, where f has continuous first partial derivatives, and let p, the point which has x naught, y naught and z naught components, be a point on S. So it's saying that we have a surface S, right? And we have equation. Equation is z is equal to f of xy, right? And then we have a point. It says we have a point, right? Now what do? We let C1, right? We let C1 and C2 be two curves. Now we take two curves that are C1 and C2, right? And these curves intersecting the vertical planes where y is equal to y naught and x is equal to x naught, right? These curves are intersecting on those vertical planes on the surface of S, right? The surface that is S, right? Okay, so then the point P lies on both C1 and C2. So basically the idea is the intersection point is this point, right? Intersection point of C1 and C2 would be P, a point which has the components x naught, y naught and z naught. All right, so now let T1 and T2 be the tangent lines to the curves C1 and C2 at the point P. So now it's really easy. It says that we take two tangent lines, one would be T1, other would be T2. All right, and these tangent lines would be at the curves C1 and C2 at the point P. All right, we just have a look over here. In the next slide, we have this particular graph, right? Okay, so it says that then the tangent plane to the surface S at the point P is defined to be the plane that contains both tangent lines T1 and T2. All right, have a look over here. So this is our C1 and this is our C2, right? These are the two curves and this is our surface. Understand? What do? We have a point over here. This is a point. This is a point, right? So we took T1, that is a tangent line in the plane, and T2, another tangent line in the plane. So it says that when we got T1 and T2, we will easily find a tangent plane in the surface S, right? So this is all about the tangent line. Sorry, the tangent plane contains the tangent lines T1 and T2. In simple words, it says like we have a tangent plane and it would carry two tangent lines, that is T1 and T2. All right, so here's the deal. If C is any other curve that lies on the surface S, right, and passes through the point P, then its tangent line at P also lies in the tangent plane. What does it mean? All right, it means that it clearly means that we can have a C3, C4, C5, C6, any number, right? We can have another curve on the same surface, right? On the surface S, we can have another curve which will pass through the point P, and its tangent line would be also lying at the point P, right? In the same tangent plane. So it means that we can have the infinite tangent lines in that particular tangent plane, right? So therefore you can think of the tangent plane to S at point P as consisting of all possible tangent lines at the point to curves that lie on our surface S and pass through the point. So the tangent line at P is the plane that most closely approximates the surface S near the point P, right? Or we can say that tangent plane touches the surface at exactly one point within the neighborhood. Is it? We can say that, right? It exactly touches the one point within the neighborhood, right? So we know that any plane passing through the point P, which has the components x0, y0, z0, has an equation of the form a into x minus x0 plus b into y minus y0 and c into z minus z0, and it's equal to 0. All right, I just explained this expression in the next slide. So here, what do we do? By dividing this equation by c, right, and letting a is equal to minus a over c and b is equal to minus b over c, we can write this equation in this particular form, right, which is z minus z naught. Now here, z minus z coordinate, it's z minus z naught is a z coordinate. Then a into x minus x naught, right? It says that this x naught is the x coordinate of our point, right? Plus b into y minus y coordinate, right? So these are actually this is gonna be a actual expression or equation that will help us to find the tangent planes, right? So if equation 1 represents tangent plane at P, right? We remember P had the components x naught, x naught, y naught, and z naught, 3 components, right? This P had 3 components. Then its intersection with the plane y is equal to y naught must have the tangent line T1. Remember we had our diagram in the last slide number 4 perhaps. So we saw that there was T1, right? But that T1 was on the point where y was is equal to y naught, y was equal to y coordinate, right? So setting y is equal to y naught in equation 1, it gives us z minus z coordinate, that is equal to a into x minus x coordinate, right? This one. And we say that we have our y is equal to y coordinate, y is equal to y naught. All right, so we recognize this is the equation in point slope form of a line with slope a. Okay, now similarly putting x is equal to x naught, okay, x is equal to x coordinate or x naught in equation 1, what do we get? We get our T2, that is the tangent line 2 in the plane, right? The tangent plane having T1, T2. So what do? We find our T2 by making x is equal to x coordinate or x is equal to x naught, right? So the equation is gonna be like z minus z coordinate is equal to b into y minus y coordinate, right? Y minus y coordinate. This is the y coordinate. All right. So what do we get? Now it says we have almost made another equation, that is equation 2, right? So it says, suppose f has a continuous partial derivatives. We have the continuous partial derivatives, and equation of the tangent plane to the surface z is equal to f of xy at the point P, right, which has x0, y0 and z0, three components. So we clearly gonna write this one, z minus z coordinate f of x, sorry, z minus z coordinate, all right, is equal to fx, where x0, y0, it would be into x minus x coordinate plus fy, which has the values x0, y0 would be y minus y coordinate, right? So this is kind of equation for the tangent planes. All right, so here we have an example. Here we have an example in our next slide. This is example number 1. So in this example it says, find the tangent plane to the elliptical paraboloid where z is equal to 2x square plus y square, right, at the point 1, 1, 3. Our x0 gonna be 1, y0 gonna be 1, and our z0 gonna be 3, right? So please give it a try and just solve it the best possible way, you know, and just try to solve it down. Okay, now so let's do it together, try to give it a solution together. Okay, what do? We say that our fx of y is equal to 2x squared plus y squared, right? 2x squared plus y2, is it? All right, what do? Then we say that our fx would be, what do? We take a partial derivative, right? And our partial derivative gonna be 4x, right? 4x. For this part, when we find the fx, it would be a constant. So whenever we take the derivative of constant, it's gonna be 0, right? All right, so here is 4x for our fx, right? Now fy would be 2y. We have y square, we just take the derivative of y square and it will be 2y, right? 2y, and we will consider this part as constant, and constant gonna be 0, right? So this is the equation we have. So what do? We just plug in the values. Our x is 1, y is 1. So what do? We will get 4 over here, right? On the other hand, we have 2y, right? 2y. Again, it's x has a value 1, y coordinate has a value 1. So our answer gonna be, for fy, it's gonna be 2. Our fx is 4, fy is 2. All right. So then it gives the equation of the tangent plane at 1, 1, 3 as, now we have this equation of the tangent plane, z minus 3 is equal to 4 x minus 1 plus 2 y minus 1. Now what did we do? We just plugged in the values over here. Right? We can see that we plugged in the values over here, and now we're gonna simplify it down, and we're gonna have our z is equal to 4x plus 2y minus 3. So that's kind of our answer, right, for example 1. So this is how it works, right? What did we do? First of all, we had to find our value of z, right? In this case we have the value of z, right? But sometimes we don't have the value of z, so what do? We just find out the value of z. After that we just simplify our fx, fy, right, and then plug in all the values in this particular equation, and then boom, we got the answer, right? So this is how tangent planes work. All right, now moving to the differentials. Okay, moving to the differentials. All right. Okay, so now recall that for a function of one variable, when we were dealing with the one variable, right, our y was equal to f of x, and if x changes from a to a plus delta x, we define the increment of y as delta y is equal to f into a plus delta x minus f a, right? So this was the kind of situation whenever we was trying to find our delta y, right, for the one variable. Now if f is differentiable at a, then our delta y is f prime a delta x plus e delta x, where e is approaching to 0 as delta x is approaching to 0, right? All right, okay. Now consider a function of two variables, because before that we were dealing with the one variable. Now here a function of two variables where z is equal to f of xy, and suppose x changes from a to a plus delta x and y changes from b to b plus delta y, then the corresponding increment of z is going to be something like this, right? What did we do? We just added one more variable, right? So what did we do? This is our delta y is equal to f into a plus delta x b plus delta y. That's all what we have done, right? And here minus f, in the previous equation we had minus f a, but here we have minus f a b, right? We simply just added one variable. That's all. We just got the equation 6, and that's how we do the differentials for multi variables, right? So thus the increment delta z represents the change in the value of f when xy changes from a b, right, to a plus delta x and b plus delta y. All right, so by analogy with 5, right, with the equation 5, we define the differentiability of function of two variables as follows. All right, so in this equation 7, what do we define? Our z is gonna be equal to f xy, then our f is differentiable at ab if our delta z can be expressed in the form, right? Now we can say that our delta z could be expressed in this form, right? Our f of x into ab, then delta x plus f of y into ab delta y, plus our e1 delta x plus e2 delta y, right, where e1 and e2 are approaching to 0 as these two deltas are approaching to 0 and 0. Same thing when we were dealing with the single variable, right? We were saying that our e approaches to 0 when our delta x approaches to 0, but here we have the multiple variables. Suppose we have two variables. All right, now what do? We have e1 e2 approaching to 0 as our delta x and delta y are approaching to 0 0, right? So that's the deal. All right, it's sometimes hard to use definition 7 directly to check differentiability of equation, but next theorem provides a convenient sufficient condition of differentiability. All right, Let's have a look. What does it say? So theorem 8 says if the partial derivatives fx and fy exist near a, b, or continuous at a, b, then f is differentiable at a, b. Right. All right. Let's see how. For a differentiable function of one variable, y is equal to f of x, we define the differentiable dx to be an independent variable. Yeah, it is dy by dx. We have been taking this thing since we're starting our differentiation, right? Whenever we were saying y is equal to fx, we were taking this dx in our values, right, to be an independent variable. So dx can be given in the value of any real number. Yeah, that's true. We have been doing that deal. Okay, the differential of y is then defined as dy is f prime x into dx. Is that so? All right, let's see how. Here we have figure 6 that shows the relationship between the increment of delta y and the differential dy. Now these two things are really different, okay? These are unique, so do not mix these two things up. All right, delta y is different and differential dy is different. So delta y represents a change in the height of the curve, right, which is y is equal to f of x, and dy represents the change in the height of tangent line. So that's a minute difference, right? One represents the change in the height of the curve, right? Other one represents the change in the height of tangent line, right? Where x changes by an amount, dx is equal to delta x, right? So all right, we just try to understand from this particular graph, right? This is our figure 6, and it says that this is change in the height of our tangent line dy, and this is the delta y is the change in the height of our curve, right? So these two things are different, and it says that they have sort of relationship when we say that x changes by an amount of dx is equal to delta x. When x changes with the amount of dx is equal to delta x, right? This delta x, when it changes, it has a clear impact on our dy and delta y, right? All right, so for a differentiable function of two variables, z is equal to f of x, y, we define the differentials dx and dy to be independent variables, right? That is, they can be given any two values. Then the differential dz, also called the total differential, is defined by this particular equation. All right, so have to remember one thing, that is, so we have to remember one thing, that when we will involve our dz, that would be a total differential. All right, it is known as total differential. So our total differential dz is gonna be fx, where we have x and y, into dx plus fy, x and y, dy, is gonna be equal to partial derivative of z with respect to x into dx plus partial derivative of z with respect to y into dy. Sometimes the notation df is used in place of dz, right? We can say df over here, we can write df over here instead of dz, right? Instead of this thing we can write df, but it doesn't really matter. I'm just telling you, sometimes if you see in the question or if you see in the equation, you have to know that this df is gonna be equal to the dz, right? So if we take dx is equal to delta x, all right, our dx gonna be this dx gonna be equal to our delta x. So this delta x would be x minus a, right, x minus a. And similarly we will have our dy is equal to delta y. It would be y minus b in the equation 10. Okay, so have to be very clear about this, because when we are dealing with the x, when we are dealing with the dx or delta x, we have to know that it would be subtracted from a, and when we are dealing with the dy or delta y, it would be subtracted from our b, right, or b. Okay, so it would be something like that. Our total differential, or dz, is going to be equal to fx of ab x minus a plus fy ab y minus b. So we just changed these two values over here. We changed these values, right, and these values, and we put these values over here in this equation. So we got this one. All right, now we have an example. Okay, there we go. We have an example. That's example number 4. And in this example it says, if our z is equal to f x of y, that is equal to x square plus 3xy minus y square, find the differential dz, the total differential, right? And we have the b part as well. In the b part it says, if x changes from 2 to 2.05 and y changes from 3 to 2.96, compare the values of delta z and dz. All right, just give it a try. It doesn't matter it's right or wrong. Please give it a try and let's see. All right, let's do it together. We have this solution over here, right? Yeah, we have this solution. All right, and solution says that definition 10 gives us something like this, right? If you remember, our dz, our derivative of z with respect to x into dx, plus our partial derivative of z with respect to y into dy. That is how we find our total differential. All right, now what do? We find 2x plus 3y, right? Because x square, whenever we differentiate x square, it would be 2x plus 3y over here, right, into dx. So this is the part 1 plus 3x, that is over here, 3x minus 2y. When we differentiate our x square, it would be 2y. It would be multiplied with dy. So we get our this part as well. So here plus this one, right? Now we're dealing with our part b. It says putting x is equal to 2, right, and dx is equal to delta x, which is 0.05, and y is equal to 3. Our dy is equal to delta y, and this value is going to be minus 0.04. What do we get? We get something like this, right? We plugged in all these values. We plugged in these values, right, over here, and then we try to find the answer. By simplifying that, we will find this as our answer. So the increment of z is delta z is equal to f into 2.05 and 2.96 minus f to 3, right? Again, plugging in the values and we simplifying them. You can check this one, right? So this is how we find our delta z, right? The increment of z. Notice that delta z It's easier to compute, right? These are the same things, all right? Okay guys, now moving to the third one, that is functions of three or more variables. Sorry for my I'd say fumbles. So functions of three or more variables. Functions of three or more variables. Now if we have w is equal to f of x, y, z, we talked about f of x, we talked about f of x, y. Now we are talking about f of x, y, z. Then the increment of w is gonna be fx plus delta x, y plus delta y, z plus delta z minus fxyz, right? You remember we just added this and we just added this into our previous equation. So that's how we find our increment of w. So the differential dw is defined in terms of the differentials dx, dy and dz of the independent variables by, this is our increment, right? We're gonna find partial derivative of w by with respect to x into dx plus partial derivative of w with respect to y into dy plus partial derivative of w with respect to z into dz. Alright, so here we have a deal. We have an example, that is example number 6, and it says the dimensions of a regular box are measured to be 75 centimeter, 60 centimeter and 40 centimeter, right? And each measurement is correct to within 0.2 centimeter. Use differentials to estimate the largest possible error when the volume of box is calculated from these measurements. Alright guys, please give it a try. Okay, here we go. If the dimensions of the box are x, y and z, right? Three-dimensional, its volume is v is equal to x into y into z, right? And so what do we find? We will have our dv is equal to partial derivative of v with respect to x into dx plus partial derivative of v with respect to y into dy plus partial derivative of v with respect to z into dz. So that's how we're gonna find our error. Okay, so yz dx, xz dy, xy dz, right? So we are given that delta x that is not greater than, or we can say that is equal to or less than 0.2, our delta y that is less than or equal to 0.2, and our delta z is less than or equal to 0.2. So to estimate the largest error in the volume, we therefore use dx is equal to 0 to, dy is equal to 0 to, and dz is equal to 0 to. Together x is equal to 75, y is equal to 60, and z is equal to 40. Okay, plugging in all those values, right? Plugging in all these values, what do we find? 1980. All right. So we find this as our answer, 1980, right? Thus the error of only 0.2 centimeter in measuring each dimension could lead to an error of the approximately 1980 cubic centimeter in the calculated volume. This may seem like large error, but it's only 1% of the volume of the box. Alright guys, so that was all about today's I'd say lecture, and that's tangent planes and differentials, right? Go through it properly, and if you have any problem, just write it down with yourself, and we will be dealing with it in our question and answer session. Thank you very much.